Hi everyone, welcome to our video on the introduction to probability with multiple events. So multiple events is where we often have like a coin flip multiple times, or we draw multiple cards from a deck of cards. Okay, so it's not just asking for one single event to occur. They want multiple events to occur. And usually, to start it off, the best way is to use tree diagrams, which we'll show in this problem right here. Also, with multiple events, we would need to make sure we know the difference between independent events. So an independent event is where the probability of the second event does not depend on the first event outcome. So independent events, these are like when rolling dice or flipping coins. Okay, and the reason for that is, let's use the coin for example. If you flip a coin, it's a 50% chance it lands on heads. While if you flip a coin again, it's still a 50% chance that it lands on heads. So whatever it lands on the first time does not impact how it's going to act the second time it gets flipped. Whereas dependent events, the probability of the second event does depend on the first event outcome. So an example of that one, let's put EX for example. Example for that one is usually like playing cards. Okay, so because the sample space is changing after each card is dealt. Okay, so well, let's say sample space changes after each card is dealt. Okay, so you'll use an ace, for example. Say, for instance, the probability that you get an ace on the first card that's given to you would be 4 aces out of 52. And then so the second time, once a second card that's given to you, well, now there's only 51 cards. And so we have a chance that not just a chance, we definitely have a different probability than the first. So it was a 52 as a denominator, and then afterwards it became a 51. Okay, anyway, let's break these down. So those are examples of them. Here we do have a coin getting flipped, and it's flipped 3 times. So the way that we're going to do a tree diagram, so tree diagrams give us the sample space and then the probabilities with them. So the way that we started off, it just starts off with these, and let's try to put this in the middle left. Okay, so you want plenty of room. The tree diagram shows just like it. So this is like at the point is nothing yet has happened, and then afterwards we flip a coin. When we flip a coin, there's 2 outcomes. It's either heads or tails. So these are the first outcomes that could occur. And then on the branches of the tree diagram, we put the probability of these happening. So the probability that it lands on heads would be 1 over 2. The probability that it lands on tails is 1 over 2. Okay, so this is the first event and its outcomes. So first event and its outcomes. Okay, and then we continue with the tree diagram. So now we look at the second event. Well, it's still flipping a coin, so we flip the coin again. Well, we kind of act like we pretended we landed on heads the first time. If we landed on heads the first time and we flip the coin, well, there's still 2 outcomes that could have occurred, and there's still 1/2 and 1/2 as their probabilities of occurring. And then we say, well, what if we landed on tails the first time? Well, if we landed on tails and then we flip a coin, flipping the coin gives us 2 different outcomes, either heads or tails. And again, those probabilities are the same, 1/2 and 1/2. So these are all of the second event that can occur. So it's based on after flipping the first coin, these are what's happening afterwards. And then from there, we just continue to branch. So it's kind of just branching after each outcome, what could happen afterwards. So after this, we would have heads or tails. After this tails, we would have heads or tails. After this heads, well, again, flipping the coin, we could have heads or tails. After that bottom tails, flipping the coin, we could have had heads or tails. And then all of these are 1/2 as probabilities because it's a coin. Okay, so sometimes we have to squeeze in those probabilities. There we go. Okay, and then now let me mark these in blue after this. Okay, so now I'm going in blue. So what this one here, I'm just going to do an arrow. This is telling us, so we follow the branch all the way to this end. When I follow it, it said that this one is heads, heads, heads. So this is the probability that it lands on heads all 3 times. And I'm just going to write it like this for abbreviation for this problem. And then what we do to get the heads is take those individual probabilities that were on those branches and multiply them out. So for this problem, it is 1/2 times 1/2 times 1/2. Okay, so I followed this branch, that branch, that branch. That was the outcomes, the heads, 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 and then their probabilities, 1/2, 1/2, 1/2, all get multiplied. And for this problem, it would be 1/8. And then we just continue that same pattern with all of these. So for the next one, I'm following the branches. Okay, so this is the probability of heads, heads, and then tails. Okay, so I followed it there. But on this problem, it's unique because they're all 1/2. So I'm going to show that one more time. That would give us 1/8. 1/8. Okay, and then following our next branch. Okay, so they're all in blue, so it's I think keeping it in blue is going to be okay. But this would be the probability of following the first top branch and then going downward to the tails and then going back up to the heads. So this is heads, tails, heads. And then multiplying 1/2, 1/2, 1/2 would give us 1/8. Okay, and let's keep it going. Okay, so the probability followed the first heads up, then down to the tails, and then another down. So this is heads, tails, tails, which is also 1/8. And then let's get these other ones. Okay, so now I'm following the tails branch down first, up the heads branch, up the heads branch. So that's tails, heads, heads, which is also, when we multiply all the probabilities, 1/8. And then we've got 3 more. That would be following the tails branch down, following the heads up, and then down the tails. So probability of tails, heads, tails is 1/8. And then we've got probability follow the tails branch down, heads branch up. So tails, tails, heads is also 1/8. And then the last one is following the tails all the way down. So it's all 3 tails, 1/8. Okay, one thing you could do to check is make sure you add all these probabilities up. So the 1/8, 1/8, 1/8, 1/8, all of these should add up. I'm going to just say sum P should be 1, which is 1/8. All of these do add up to 1. So that's a way to check that the table is correct. If we have everything marked, every possible thing occurred in it. Okay, so let me mark these. I forgot to mark this. So this was our third event. Now in these letters, this is the order that the coin landed on. So this is the first coin. This is the second coin. And then that's the third coin. So it's showing the order of how the coin landed. And that's true all the way down. So like this, so the second one would be it landed on heads first, heads second, and then tails third. So it's showing the order as well. Okay, so it's showing every possible thing that could happen. Okay, and now that we have all this information, we should be able to answer any of these random questions about the coin flip of 3 times. Okay, so for number 2, well, it did ask, are the events independent or dependent? These are independent. We mark that up there. So coin flips are independent. So the first coin flip does not impact the second coin flip. Okay, so those probabilities for each individual landing on heads and each individual landing on tails is always 1/2. Let's see these other questions. Okay, so for number 3, find the probability that the coin landed on tails all 3 times. Okay, well I'm just going to mark it in green. That's this one. So that's why it's all nice and marked. I'm all done. It's 1/8. Okay, moving on. So that's our final answer. Moving on. This one, it says find the probability that the coin landed on at least one tails. Okay, so let's use a different color. Let's do it in orange. So at least is one of our keywords. At least one tails. That means one or more tails. Okay, so that means I'm looking at all these probabilities that have one or more tails. I'm going to go ahead and put a big open or closed circle on all the ones, or let's underline it. So there's at least one tails. Here's 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 at least one tails. So it's all of the ones that have at least one tails pop up in this final probability to the right here that we marked. So that's all of these 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, and 1/8. So I have 7 of those 1/8s. So this probability of at least one tails, I'm going to write it like that. At least one tails is 1/8, and there were 7 of them. So I'm going to show the 1/8 times 7, which is 7/8. There we go. Another strategy for at least one that can be useful for us. I'm going to do it right here. Let's mark it. We'll just mark it in purple. Okay, so here's a rule that can help. So the probability of at least one, I'm just going to say blank. So because the blank changes from problem to problem. So this is useful. So on ours, this at least one tails is 1 minus the probability of no blank. Okay, so whatever that blank happens to be, so I'm just trying to break it down into words. So for instance, on this problem, the probability of at least one tails, I'm going to put it in the purple right underneath, is also equal to 1 minus the one probability that didn't have any tails in it, which was that one, the 1/8. It's all the one that has nothing but heads landing up. Okay, so 1 minus 1/8 is 7/8. So it's another way to do it. Okay, so it can be useful to speed up time depending on the problem. Okay, so that's how we do these tree diagrams. All right, let's see. Let's do one other in this video. Okay, so if you need a break, take a pause. So here we've got cards, though. Okay, so I'm going to do another one where it's 2 cards are drawn from a well-shuffled standard deck without replacement. Okay, so that's typically how cards are done. So the without replacement means that you get one card and then they just give you another card right away. If they said with replacement, it's like they're giving you the card and you write down what card you got and then you give it back to the dealer, and then from there you draw another card. So that's weird. We usually don't play cards like that. So this is the standard way to play cards. Okay, so anyway, so find the probability of the following: drawing a spade and a heart. So this and, here we have to be careful because it is multiple events. 2 cards are drawn. So what they're saying is you need to get a spade and a heart, and it doesn't say the order. So it's saying we could have first a spade, second a heart, or we could have first a heart, and then the second card could be a spade. So that's how we could break it down more formally with our language. Okay, anyway, the way that I'm going to break this down, okay, so since this first one is involving suits, I see spades and hearts, so suits are important to us in this scenario. That's how I'm going to break down the tree diagram. Okay, so I'm going to do, let's try to give ourselves plenty of room. Okay, so we've got spades, we've got hearts, we've got clubs, and we have diamonds. And it really doesn't matter the order that you do this in. It just however way you prefer it. Okay, so this is the first card being drawn right here. First card. Okay, so the probability that I'm dealt a spade, so here's where we have to remember there are 13 spades out of 52. Okay, so that means I have 13 spades out of 52 right here. And then, well, moving on to the next suit, well, all suits have 13 in them. So all of these are 13 out of 52. As our probabilities. Okay, so there's the 13 out of 52s. And then now I want to continue with my tree diagram. Well, here's where, so this tree diagram, if I continue splitting it up, I'm going to erase this in a second. If I do this with all of them, it's going to get a little too messy. Okay, so there would be 16 different things that could happen. Okay, so what I'm going to do on it is let's erase it. Let's only focus on what's really important. And even here, you can almost get, since the clubs and diamonds aren't important in our problem, we can kind of scratch those out if we don't want them here in this problem. Okay, so I'm only going to focus on the spades and the heart from here. Okay, so again, you could list it all out, but it takes more time to write. So let's only think about what's happening with the spades and the hearts. Okay, so the spades and the hearts, that's all I care about on my second card. So this is the second card that's given to us. Okay, and now I want to find those probabilities. Well, there is one less card, so that means the sample space will be 51 for all of these. Let's go ahead and mark that now. Okay, so the sample space is 51 on all of them. And then now we just think, well, based on this top branch is saying I got a spade first. So that means I would have one less spade. So instead of 13 as my numerator, I would only have 12 there. Okay, but this bottom branch for the second card, if the first card was a spade, that means I still have all 13 hearts that I could have chosen, or that I could have been dealt. Okay, so notice that probability. So 12 out of 51 and 13 out of 51. So they're different probabilities because we have, in this case, let's go ahead and say, we'll mark it to the side. Here, this is dependent events. So the probability of the second event does depend on what happened on the first event. Okay, and then let's fill these other two in. Well, my second branch is a heart. Here, if my second card drawn is a spade, well, that means there are still 13 total of those, so 13 out of 51. But if my first card was a heart, then the second card being a heart, there would only be 12 of them. That could happen, 12 out of 51. Okay, so again, the probabilities are different. That's okay. That's what should be happening. Okay, and then now what we've got here, so drawing a spade and a heart. So this is the probability of drawing both spades. I don't want both spades, so I'm just going to cross that out anyway. This is one that I want. Probability of a spade and then a heart would be 13 out of 52 times 13 out of 51. And then this I think we'll use a calculator for. The next one is also one that I want. This is the probability of a heart and then a spade, which is, based on these probabilities, 13 out of 52 times 13 out of 51, which again we'll need a calculator for real quick. Okay, but then afterwards, this one would be the probability of both being hearts, which I don't want. I want one spade and one heart. So I'm just going to cross that out. I don't need it anyway for this number 1. Okay, so that's how we can break these down. And then let's go ahead and get a calculator going for this one. I'm just going to use this scientific one that's on the computer. Okay, so we'd have 13 divided by 52 times 13 divided by 51. And we get that. Okay, so 13 divided by 52 times 13 divided by 51 is 0.0637. We'll round it to 4 decimal places. 0.0637. And then this actually is the same multiplication. You can see 13, 13, 52, and 51. Okay, so that's the same. Okay, so drawing a spade and a heart, again, it could come in any order. Our final probability, since it doesn't say the order, we would need to add them up. So our final probability is the spade or the heart plus the probability of a heart or a spade. Okay, so these are the two cases that we had. So we should add them up for our final answer. So notice that, and this is technically or, notice the way that we treat and with multiple events versus a single event. So with and in these multiple events, this is how that gets broken down. Same deal with or. Or is treated a little bit differently too in these multiple events. At this point, or is addition. Okay, so the and part is just to tell you to do a tree diagram. I'm using the word or. It doesn't say it anywhere, but this is what could have happened. It's saying first a spade and then a heart. Let's put or after this point. Or first a heart and then a spade. Okay, so the or would be add those given probabilities together. Okay, and when we do, let's go ahead and write those together. Okay, so that I'm also using my calculator for, so I need to add 0.0637, which gives us 0.1274 to 4 decimals, 0.1274. Okay, so there it is. Okay, so that's how we break these down. Let's see this next one. Okay, so one more in this video. So this is drawing 2 aces. Okay, so this time it's not about suits. It's really what's important is the value of the cards. Okay, so, or since it's only talking about aces, I'm going to say for my tree diagram, let's do ace and not ace. So I don't want to do all 13 different values. So 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. I don't want that. Since ace is the only thing that's important to us in this problem, I'm going to do ace and the complement of the ace. Okay, so and for an ace, so now we're thinking the first card is an ace and the second card is an ace. Well, our probabilities would be 13 out of 52 for it, or not 13, sorry. I'm thinking suits still. There's only 4 aces in a deck of cards, so 4 out of 52. And then, well, the non-aces would be 48 out of 52. And then now let's branch it again. Ace and not an ace. And let's go ahead and set the other one up. Ace and not an ace. Okay, so following this top branch, this is as if an ace has already been drawn. So that means I would have 3 aces left out of 51 total cards. Well, if an ace was already drawn, the probability that it's not an ace would still be 48 aces, but out of 51. And then following the tree diagram down below, it's as if the first card is not an ace. So that means the probability that the second card is an ace is 4 out of 51, because there's still 4 aces. But the probability that it's not an ace would be 47 out of 51, because there's 1 less ace and 1 less card. And then so, for our problem, all we care about in this is 2 aces in a row. This is the only place that it happens. And so that means we could just multiply the 4 out of 52 times the 3 out of 51. And so that would give us our final probability. I need my calculator again. I can't do that. Okay, so let's move it on over. So 4 divided by 52 times 3 divided by 51. Okay, so that's it. So it's 0.0045. Okay, so usually they do decimals for these style problems, and often they want it to 4 decimals. Just be careful when you answer it in the homework. Make sure to round it to whatever they want you to round it to. Okay, anyway, so that's our multiple events for now. So most of the time it's making these tree diagrams. Notice we can make adjustments to them. Okay, so like on this one, I scratched out a bunch of junk because it wasn't going to be important for the rest of the problem. Same deal with this one. I didn't want all of the values listed. I only said, well, let's do ace and not ace. And then from there, also, I didn't find all of the probabilities because I don't need to. Okay, so it just depends on what they're asking for what you need to carry on with. Okay, so that's it, though. I've got more to try. So if you're stuck, I mean, that's okay. We'll get more practice on. Okay, so thanks for watching, though, and I'll see you again soon.